Okay, and in fact, if I'm not mistaken, units 2, 3, and 4 are all about derivatives. Okay, we have 3 big topics: limits, which we've already done the majority of stuff with that. We'll hit them here and there, but limits. We have derivatives, which we're going to spend, again, I think it's like 2, 3, 4. And then we have integrals, which maybe start at 5. So, but I think there's 8 units, so I don't remember exactly. Okay, so kind of introductory here. Some definitions, vocab, and starting to look at, it'll take us a couple lessons before we totally get to derivatives, but starting to look at some of the lead-in pieces. So, okay, as we look through here, in plane geometry, as in flat 2D geometry, right? We learned that a secant line is a line that intersects a circle or some other curve in 2 places. We also learned that a tangent line is a line that intersects a circle at 1 point. Do you remember that vocabulary? Okay, where a secant line does that, right? However, a tangent line does that. Does that sound familiar? Tangent line is probably the one that I would think you remember. I'll be honest, that's the one I remember the most. Tangent line is the one that touches a circle or touches a curve at 1 point. A secant line just crosses through it. It's not necessarily a diameter or anything. It just crosses through and intersects in 2 points. Okay? So a little bit of vocabulary. And I'm going to tell you guys, this whole tangent line thing, we use it a ton when we talk about derivatives, because it's involved in the definition of derivatives. So, okay, in our study of differential calculus, we need to clarify, classify, and truly understand these 2 big ideas. For general curves, we need a better definition. We'll be concerned with the tangent line drawn at a point on a curve. Okay, most of us believe that a tangent to a curve is a line that intersects the curve at exactly 1 point. However, in this figure, you can see the tangent line touches the curve at several points. So a better way to describe the tangent line is a tangent to a curve at a point is a line that best models or approximates the behavior of the curve at that point. Okay, so as you look at Doug's quartic curve here, okay, if you remember from pre-calc, this is what an x to the 4th, this is one way of what an x to the 4th graph could look like. Does that sound familiar? Mm-hmm. Okay, x to the 4th was, we've talked about that a little. Didn't that come up at some point this year?
Yeah, we talked about it.
Okay.
It does the things on it.
Yeah, because it could be just a flattened out parabola, right? Mm-hmm. Or it can be some version of a W, which is what we have here. Okay. So, the idea of a tangent, okay? I drew a tangent up there, and that's what you tend to think of, isn't it? If I draw a tangent here, that's not perfect, but, you know, like that might be a tangent, right? However, what we're looking at here is that right over here on this right side of this quartic, this situation at P, that line is tangent to the curve at P. Okay? It runs along with the curve briefly. It's usually going to describe the slope of the curve at that point. Okay? That's what the tangent line, that's where we're going to go with this, is that a tangent line describes the slope of the curve at that point. Whereas over here at point Q, those are just 2 intersecting lines at point Q. Okay, there's nothing there. They're just 2 intersecting lines. Over here, this is tangent because it runs briefly along with the line, or the curve, if that makes sense. Okay, so understanding tangent, as I said, is a huge, huge thing. The fact that it approximates behavior of the curve, a lot of times we're going to think slope. Okay, so notice, I'm getting ahead of myself. This idea will help us find the slope of the curve at the point. When we talk about slopes of a line, an entire line has one slope, doesn't it? Mm-hmm. Because it's going at the same angle. This curve, does it have the same slope all the way around? No, it has an ever-changing slope. And so when we find a tangent, it helps us decide the slope of the curve at that specific point. The slope of the curve at a specified point will be referred to as the slope of the tangent line, the instantaneous rate of change, or the derivative. Okay? I mentioned that derivative is, you know, where we're going here. But when we talk about this, it's the slope of the tangent line Instantaneous rate of change, derivative. Instantaneous being the rate of change at that instant, if you want to think that way. Okay, so it's the slope of the curve at that instant, at that point. Most important thing to note here is that the tangent to a curve at any given point is unique. A function f that has a defined slope at x equals a has two things in common with its tangent at x equals a. Okay, one of those, so the point of tangency right here, if it's going through a, that point of tangency is going to be a comma f of a, because your y value is going to be whatever you get when you plug the x value in. Is that making sense? Okay, and then the slope at the point of tangency denoted by f prime of a. So there are several ways to show what a derivative is, okay, to state that something is a derivative. One of the biggest ways is to use this little prime mark here. It looks like a single, I want to say a single quote mark. It looks like kind of like an apostrophe, right? Okay, but it's just a single quote mark or whatever. Read f prime of a, that denotes the derivative. Well, if you're catching on here, the derivative of something is the slope of the point of tangency. Okay?
Did we learn the prime mark in geometry or something?
I think we learned it in
Or was it
chemistry.
chemistry? Oh,
Chemistry and AP Bio, and
But I think you've probably used it for other things,
that makes sense.
just because you wouldn't have talked about derivatives in those
Yeah.
classes. Does that make sense?
Mm-hmm.
I mean, we could also talk that it looks like f feet, right?
That's awesome.
You know, if you think
Oh,
inches
yeah.
versus feet.
Like 5.
oh yeah,
Yeah, but it's not a feet. It's prime. It means derivative. We'll learn a lot more about that in the day stuff come. Okay? So, boxed thought here. Any function with a defined slope at a specific point will have one and only one tangent line at that point. Okay? So, when we talk about this point at A, there's one official line that is tangent at that point. It's not like, oh, well, this one's tangent, this one's tangent, this one's tangent. No, as you get different tangent lines, those are changing the point that it meets the curve with. Okay? So that's some information there. Keep talking?
No.
Yes.
I didn't want you to be done.
I forgot to ask. I'll give you a real answer.
Okay, so we are going to spend some time here on the top part of this talking about average rate of change in secant lines. And then we're going to talk about instantaneous rate of change and tangent lines. Do I only have one copy of this page loaded?
Are we going to get through all the notes today?
No.
Okay, I think so.
Okay, I do only have one of this page loaded. I think I must have accidentally deleted one this morning. Okay, a secant line. I already talked about when a secant line crosses through a circle, it touches it in two places, right?
Mm-hmm.
I guess, I don't know, is the diameter technically a secant line? I don't know if secant has a different definition that says, other than, I guess the diameter is technically a secant because it touches in 2 points, right? Okay, so a secant line is a line joining 2 points on a function. So right here, PQ, this is a secant line, okay? It cuts through the curve, touches it at 2 points. Finding the slope of the secant line through 2 points, so they're calling points P and Q, which points P is at A, so A comma F of A. Point Q, they're saying it's at B, so B comma F of B. Will give you the average rate of change over the interval from A to B. You have known how to do this since your first algebra class. We just have new notation. I want to even say you might have done this in pre-algebra. I feel like you maybe did slope in pre-algebra, maybe not. But
I think we did with Mr.
I
Bove.
think we did it in pre-pre-out.
Like with Miss Pace.
Yeah, it was
My
pre.
I don't know.
pre-algebra class was like whack,
Mr. Bove
so
doesn't count.
Okay.
most likely not.
So-
We had COVID.
anyways, so average rate of change, folks. Average rate of change refers to a secant line, and it's referring to basically, you can think of it, it's finding the slope or the average rate of change between those 2 points. So it's not just at one point. That will be down here when we talk about instantaneous, but it's the 2 points. in order to do average rate of change, how do you find slope?
Rise or run.
Okay.
Yeah.
So rise or run, but I'm not talking about looking at the graph here. So then we go y minus y over x minus x, right?
Yes.
Or as Doug said, y2 minus y1 over x2 minus x1. Also, I think I've mentioned this earlier in the year, delta y over delta x, which that's the short way of saying change in y over change in x. Okay. So AROC, have I talked about AROC this year?
Yes.
AROC came up, didn't it?
AROC and IROC.
Okay, so we're talking about AROC and IROC. They're back. So AROC is average rate of change. It's a slope, change in y over change of x. We know M stands for slope, right? So this is saying slope of the secant line. And notice here, f of b minus f of a over b minus a. That's doing your y minus y over x minus x. So all of that right there is when we're talking about this average rate of change and slope of the secant line, okay? Same thing when we talk about it. So example 1, find the average rate of change of f of x equals x cubed minus 3x over the interval 1, 3. Find the average rate of change. What are they asking me to find then? What? Did Hannah say what I think she said? No? I thought I heard something over there, but okay. Okay. It's average rate of change is AROC. They're asking us to find basically the slope of the secant line. Okay. That's what I guess what I'm trying to say is when you see that terminology, average rate of change, think, okay, I just need slope of that secant line. Now, what do we know? My x values are what?
1 and 3.
1 and 3. So I need to know 1 comma something and 3 comma something. How do I find my somethings?
You plug in 1 for x and you plug in 3 for x.
You plug it into the equation.
Yeah.
Plug it into the equation, yes? That's what he was saying. So we're going to find, I'm going to write this as f of 1 and f of 3. Trying to use proper terminology here, yes? So with that in mind, I don't know, do some math. 1 cubed minus 3 times 1 is going to be,
-2.
What?
-2.
1 cubed is 1,
I'm stupid.
3 times 1 is 3, 1 minus 3 is -2. AKA you found your careless mistake is really what you're saying?
Mm-hmm.
Okay. F of 3.
18.
I have no idea. 27 minus 9?
Give me
That's
some.
18.
18. You guys had worked ahead of me? Good.
Yes.
Okay. So again, they asked us to find AROC, which means I'm finding slope of the secant line, which means I'm doing what?
3 minus 1 over 18.
No. 18 minus -2 over 3x1.
Change in y over change in x. So we have to use the y values. So 18, minus -2 over 3 minus 1.
See, I thought what I wanted to do, like in the beginning, was wrong, but we get to the same place in the end. Because I was just like, okay, put the f of x into like where f of b is. So, but it's literally all the same.
Yeah. I mean, really what we just did here is we just did f of 3 minus f of 1
Yeah.
over 3 minus 1. That's what we really just did, isn't it? I didn't write it out that way, but we could have. Okay. I could have really streamlined that a little bit, but I didn't. Okay. Average rate of change. Think slope.
Gosh, that was so
Slope of the
easy.
secant line.
That was easy.
Let's keep it like
Okay.
that.
It's a matter of interpreting what they're asking, though. That's, where we run into the problems. Okay, instantaneous rate of change in tangent lines. Finding the slope of a tangent line at a point. So notice we're talking at 1 point. We're not talking secant line where it crosses through the curve at 2 points. We're talking tangent at 1 point, right? Find the slope of the tangent line at a point will give us the instantaneous rate of change at that point. So here, instead of slope of the secant, it's slope of the tangent line, and it's instantaneous rate of change, or if you remember from first unit, IROC. However, we only have a single point, so using the average rate of change formula will produce an indeterminate form, right? Because if we're trying to find the tangent or the slope of the tangent line at point A, you don't have a B minus A here, do you? It's just A minus A, which is 0 over 0. That's one of our indeterminate forms that you don't just stop and say no solution or anything like that. You have to come up with a plan B.
That's how I got. I just put Danny. 0 over 0.
I will say there were some people that
I
thought
also did that.
anything that didn't work out at all was just D and E.
All right.
Okay.
That was a problem.
It was a little rough. I could not figure out, and I was like, how the
On the flip side of it, when you get stuck, I think what it turned into is, well,
D&E.
I'm stuck. I don't know where to go. D and E.
I can't sit on this question the entire time.
I can't sit here and stare at it. It's not gonna. The answer's not gonna match.
Okay.
On the
I ended
face
up doing that though.
Moving on to plan B. Okay? Because we can't do slope of the tangent line with just one point. So now, plan B. Let's choose a second point that is extremely close to our point of tangency. We can call it point Q. Then we can algebraically estimate the slope of our tangent line. All we need to do is add a really small amount. That really small amount we're going to call H to our point P in order to create that arbitrary point Q. And this would give us technically a secant line, even though the 2 points are like so close I can't even draw them. Okay? Excuse me. Now, okay, so as we look at example 2, I'm realizing the points aren't on my picture, are they? They're not on your picture either, I bet. Okay. Use the 2 points P and Q, which they're labeled but not there. P and Q in the average rate of change formula to find the slope of the secant line. If we move point P directly on top of point P when H goes to 0. Okay? And so this is where, as something gets closer and closer and closer, this is where I said, yes, we're moving on from limits, but yet they still exist. Okay? So, with that in mind, notice it says use average rate of change, yes? So we're going to use AROC. Now, I guess the idea here is, so here is point P. Okay? Here, above H, is point Q. The idea of instantaneous rate of change is that we're looking at this as this point gets closer and closer and closer to the other point. Like, they would end up on top of each other, essentially, as it mentioned. Okay? Okay, so finding the slope of the secant line, we don't have numbers here. Okay, that's what it is. We don't have numbers here, so we're going to think about it as setting it up with just this information here. So if we have, what do we have here? We have x, y, yes? So if we think about average rate of change being change in y over change in x, or what are my y values that we're using here? F of a and f of a plus h. I'm going to reverse that, and I'm going to say f of a plus h minus f of a. If I do that, what does my denominator look like?
A minus A. Is what it is up there. How do you change?
Okay, so we're using the x values. The one x value is a plus h minus the other x value, which is a. What does this clean up to be? The top stays the same.
Over H.
Over the bottom becomes h. right there, and mine is written sloppy because I'm trying to squeeze it in a place where I don't have the room because I didn't zoom this out, or zoom this in, I mean. Right there, we don't know it yet, but we're going to pair that with a limit, and that's going to be our definition of derivative. Okay, that's going to be the idea of trying to find the slope of the tangent line by looking at 2 points that are getting closer and closer together. Yeah. So I'm trying to think of the best way, like the idea is if we're trying to find the slope of the tangent line at A, that's horrible. We're trying to find that, right? Well, what's happening is this point right here is getting closer and closer and closer to the point where they're going to end up right next to each other, essentially almost on top of each other. Okay? And I guess I have a note in my notes that says, can move H closer and closer to A. And then in parentheses, I'm going to tell you that that is a limit. Okay, so those are limits that we're talking about. Okay, moving along. Okay, although the slope of the curve is always changing, talked about, every point of the curve is going to have a different slope. We know the slope of any line is constant, even our tangent line. So let's apply the limit rules, just talked about this, right, to our rate of change. As h approaches 0, we can use our algebraic techniques and then evaluate the limit to find the slope of the tangent line at that single point. Okay, so you have in this box slope of a curve at a point. It's slope of a curve at a point because the distance between those values is approaching 0. Okay, so this is that fraction we just came up with, right? Paired with a limit. Again, we're not officially calling it a derivative yet. I'm trying to think. I want to say we don't officially really use the word derivative until like 2.2 or 2.3 maybe. No, we use it in 2.2. Okay, but this is where we're leading into. Okay, so the slope of the curve y equals x at the point P is whatever that is. Okay, so slope of the curve. This is the slope of the tangent line. Derivative, slope of the tangent line, 1 and 1. Okay. We're going to work some with the difference quotients today. So the fraction that's within the limit here, f of a plus h minus f of a over h, is the difference quotients. Let's find the difference between those. Using algebra, your goal will be to simplify the difference quotient. Then you can evaluate the limit as h goes to 0. This exercise will produce a number value if you correctly divide out the h in the denominator. We've already done this once. You didn't like me much for it. It was on the review worksheet. That one I did at the end of class. Yeah, it was the bottom of that first page.
Oh, that one.
Okay?
Yeah.
It all worked out nicely in the end, but it was a little intimidating at the beginning. Doug says 4. That sounds about right because it was bottom of the front page. That's definition of derivative. Now, here's the good news, guys. Definition of derivative is a short-lived thing in that we first learn how to do derivatives using that big old kind of nasty limit at times, right? But then we learn how to use the derivative doing a lot of shortcuts and make it really nice. Okay, we have a lot of derivative rules. So using the difference quotient. Using a difference quotient correctly has some challenges and pitfalls. So let's be sure you understand the notation. I'm going to the next page, I think. Yeah. Okay, so this is very basic, but very important. For each function below, find f of a and f of a plus h. Nothing fancy, but it can be done wrong. So we're being asked, what is f of a? What does that mean? You guys hear me say this all the time.
So is it like y over x? Is that all?
F of x is defined to be 1 over 2x. We're being asked what is f of a?
1 over 2a.
Because I'm going to say every place I see n
Oh.
x, we're going to replace it with whatever's in here, which in this case is a. So f of a is going to be, instead of 1 over 2 times x, it's going to be 1 over 2 times a. Okay, so whatever's in those parentheses goes in the place, every place you see an x. Now, here's the tricky one that we have to learn how to work with. F of a plus h. Every place I see an x, I'm replacing it with
A plus a.
a plus h. Whether you see 1x or whether you see 10 different x's. Every time gets an a plus h. So in this case, it's going to be, instead of 1 over 2 times x,
1 over 2a plus 2a.
1 over, I'm going to say 2 times a plus h to get us started. How do I have it written in my notes? Honestly, my notes, I left it just like that. Now, could you distribute
Yes.
and say 1 over 2a plus 2h?
So then you don't put it into that big equation up there?
We're not doing that right now.
Oh.
The directions are only asking me to find
Okay.
f of a and f plus a plus h before we get to that big equation. Don't worry, we'll get to the big equation.
Yay.
Okay, so B. F of x is defined to be the square root of 3x minus 2. So what's f of a?
Square root of 3a.
Are we good with that? This is not supposed to be a difficult part right here.
I feel like
Now.
I was overthinking it.
Probably.
That's what I wanted.
Now, f of a plus h increases the difficulty level a little bit, but
3, and then in parentheses, a plus h minus 2. Yes.
all under the
Square root.
square root. So square root of 3, and then it's supposed to be 3 times x, but what am I putting in place of x?
A plus h.
A plus h minus 2.
Why is this easy?
Because we're just doing a small little bit.
Right now.
But here's the deal. If we don't understand this later on, that's a good way to put it. I mean, you're really going to have a lot of problems. So that's why we're trying, it actually breaks it down to the basics. So now, I probably did clean this one up. Actually, no, I didn't clean this one up either. Shocker. I guess because it's not going to be able to add. So you could say square root of 3a plus 3h minus 2 if you wanted to, right? Okay, C. Now, I will tell you, I did clean C up.
Okay, that's what I thought. I was like, did you clean C up?
Yeah. Okay. First of all, get the easier one out of the way. What is f of a?
2a minus a squared.
Good? Okay. Now, beginning step with f of a plus h. Okay, so instead of 2x, I'm going to write 2 times a plus h. Instead of minus x squared, I'm going to write
A plus h.
Are we good? Now, and I don't know why I have this one multiplied out and simplified and the others I don't, but this is going to be a necessary step to be able to clean this stuff up. So the first part is easy. 2 times a plus h is going to be,
2a plus 2h.
okay. How awesome do you feel right now?
So
Can we do this all in our heads?
No, I did it out of the paper,
A
but
squared plus 2h.
Oh my.
plus 2AH.
Okay, so
Yeah.
first of all, a plus h squared means we're going to have to FOIL. Is that what Hannah forgot? Okay, I hear you over there yelling at yourself. So, okay, so we're going to FOIL. On top of FOILing, though, we're also subtracting the quantity, yes?
Oh no!
So,
Man.
what's my first terms? A times a is
A squared.
a squared. So we're going to say minus a squared. Then we do our outsides. It's going to be AH. When I do my insides,
AH.
AH. Outside AH plus inside AH makes it
2a.
2AH, but we are subtracting, so
Negative 2a.
minus 2AH.
I can't forget that step.
And then last, h times h,
H squared.
Squared.
but we are
Subtract.
subtracting,
Minusing it.
so minus h squared. Now, obviously, could you have written a step or two out there in the middle if that was better for you? But I think you guys all followed one way or the other eventually.
Yeah.
Once you corrected mistakes. Okay, D. What's f of a?
3 over a plus 1.
Good. F of a plus h.
3 over a plus h
That's one.
plus 1.
I'm good. That was kind of easy after C. Like, wow.
I like our old ones.
I love doing equations like this, like just plugging things in.
I could solve for x all day. It's
I
maybe like
love
limits and
plugging
stuff.
and chugging.
Yes.
Okay, we're ready for the next part.
Okay. That's a big one.
Given the function f of x equals x squared, use the difference quotient to find the slope of the curve at the point 3, 9. Okay. What is going to be the best way? Okay. So, first of all, in order to find slope, we're going to use the difference quotient. So it's the limit as h approaches 0 of f of a plus h minus f of a all over h, yes? We had defined that on the previous page. We are provided f of x equals x squared, and eventually we'll get to the 3, 9 bit. So, we want to find the limit.
Sorry, guys.
We want to use that f of x definition that we have. So, okay. It's still going to be, until we put in 0 for h, it's going to be the limit as h approaches 0. What's f of a plus h? How do I write that?
F of a plus f of h minus f of.
Um,
Well, I guess you can't split them. Never mind.
F of a plus h. This is what we just did on the other page, guys. What is f of a plus h?
a plus h squared,
X squared.
Ace.
or a squared plus 2ah plus.
Save that for the next step.
Okay.
I'm looking for,
I thought you were trying to combine the two when it was a negative.
okay, so f of a plus h means every place I see an x, I replace it with the quantity a plus h. Since this is x squared, I'm going to say a plus h squared. Good? Minus, what's f of a look like?
Ace squared.
A squared.
A squared.
Every place I see an x, it becomes a, so this is a squared. All over h. Now, if you plug in 0 right now, we go to that fun indeterminate form of 0 over 0. However, if you do the algebra here, life will be grand. Okay, so a plus h squared means we need to officially FOIL. So that's going to be a squared
Plus 2ah
plus 2ah
plus h squared
plus h squared
minus h squared
minus the other a squared
over h.
all over h.
The a squared and the h cancels the one h.
Oh, the h does cancel.
Which is always going to happen if you're doing this right. Now, for the moment, I'm going to take this as 2 steps. So I'm going to write this as 2ah plus h squared over h. Okay? And you don't have to. Now, to show my next step, though, I'm not going to just cancel them. I'm going to do the official route of on top there is a GCF of
H.
h. So officially I'm going to factor h out. Then I have 2a plus h
Over H.
over h. And now this is where I will officially cancel my h's. And so that makes my problem the limit as h approaches 0 of 2a plus h.
Oh yeah.
Well, okay, so,
because that it messes you up if you do it the way that I did it.
okay, so hold on a moment. We're not worrying about 3, 9 yet. Right now, I just want you to take the limit. And I think I'm going to come over here. Limit as h approaches 0 of 2a plus h. How do I take the limit?
You put
Plug in
put
zero.
a 0 in.
You plug in 0 for
H.
h because it's as h approaches 0. And so then this becomes
2A.
2a plus 0, which is 2a. And what was this that we were finding? There's a limit, but it is our slope. Okay? So our slope, what this is saying right here, is that our slope of a tangent line on f of x equals x squared at any given point is going to be 2a. Okay? Now, and I think it looks like I have that written in my notes, that this is the slope formula for any value of x on y equals x squared. Slope formula for any value of x on the equation f of x equals x squared. Okay? Now we're not done with this problem. Question?
Yes. So I keep on accidentally writing as x approaches 0. Would that be counted off on the AP test if you do x instead of h?
Well, multiple choice, it's not going to matter. I mean, unless you're picking and they have, you know. In terms of like free response, I don't know. Okay. I will say I sometimes get a little nitpicky about it on test, just because I need you guys to know that definition. Okay. And it's something that just takes a little practice, right? I mean, this is day 1, so. Okay. Now, this said, given the function, use the difference quotient. It didn't say to find the slope of the curve at any point. It said specifically at 3, 9. So if we're doing this at the point 3, 9, they want slope, yes? So what are we thinking here? Three, 9, what is 3? 3 is your x. Also, I don't have a spot to plug an x in. It's your a, right? In other words, this is kind of the idea of a comma f of a. Okay, that's what that is. So in order to find my slope at 0.39, how do we find slope? 2 times a, which is 2 times 3, which is 6. So we have a slope of 6. Now, I didn't give you a visual. You guys know what f of x equals x squared looks like, right?
It's a problem.
It's parabola. I just drew the 1/2 of it. 3, 9. I'm picking a random point. Could that be 3, 9? Sure. What does this 6 represent? Slope of the tangent line, right?
Yeah.
So right here, there's my point. The tangent line looks something like that. And so we're trying to find the slope. I'm going to say m sub tangent, slope of the tangent line. Okay. Questions?
Not really.
Okay. Because we just did derivatives the really long way. We'll learn a lot shorter ways, don't worry. Okay. I think we can do this next one real quick. Yes, let's do it because it ties in now that I remember what it is. Remember that writing the equation of a line requires a point and a slope. We're going back to very first algebra here, right? It follows that we should be able to write an equation for the tangent line through a given point since we can find the slope by using the limit process and we're given either a point or an x-coordinate. In calculus, notice here she says we'll focus on using point slope of form of a line. But this point slope form of the line looks a little different than what you're used to. Okay, so point slope form of the line. When we learned point slope form of the line, we used what? Y minus y1 equals m times x minus x1. And here's what I'll say, guys. In calculus, unless it specifically says express your answer in this form, which it rarely does, what she has would be okay. What I wrote would be okay. Y equals mx plus b would be okay. Okay, there's not usually a specific, like you have to use this form. Now, what it is being able to recognize this form, okay? So what she has here comes from what you originally learned. I know I taught it to you in Algebra 2. Point slope is one I don't know. I think Mrs. Roger teaches it in Algebra 1 now, but okay.
Oh, you're just taking.
Yeah, what is this doing?
Taking it over.
You're just,
moving
instead
over.
of y minus y1, add the y1 over.
Oh, well that
Yeah,
makes sense.
it's like
That's the same thing. Almost.
Sorry.
At
Okay, are we there now?
first I was like, oh, that's kind of weird, and then now it's fixed, and I'm like, oh.
Are we making the connections now?
Yeah.
Sorry, I thought the connection was made. Obviously, I was mistaken.
You gotta give it a second.
Okay, the connection is made now. Just the fact that her form is just having the minus y1 added over on the other side. Okay, it's very similar. Now, write the equation of the tangent line for y equals x squared at the point 3, 9. So we got a point. What else do we need to write the equation? A slope. We have our slope?
Yes.
Oh yeah, we have our slope. What is it?
2a.
2a.
X squared.
6.
Oh, because it's
Where are all these random pieces coming from?
up there.
The previous problem, yes?
I got it now. I'm there.
I know, I can
Yep.
tell. We are not all there by the... Because you guys said 2a, and I'm like, okay, well, the slope of any tangent line is 2a. But the slope specifically at 3, 9 was
6.
Oh, the slope of any tangent line, like of that.
of this curve.
Okay.
So anytime you have y equals x squared, the slope at any point on y equals x squared will always be 2a,
Okay.
the slope of the tangent line. Now,
There now.
give you a different curve, that equation changes. Okay? Now, we're asked to write the equation of the tangent line for y equals x squared at the point 3, 9. Can we do it?
Well, we already have everything. Just write the equation.
Okay, let's do it.
Y equals 6 x minus 3 plus 9.
Whoa.
That was all you had to do for that, bro?
Oh my gosh.
Now, if you're listening to what Kylie said versus what I wrote, I put a set of parentheses in there that she didn't really say.
Yeah, I didn't say differences, but I have
Okay,
it too.
so it is 6 times the quantity x minus 3 and then plus 9. Okay,
Do you want us to like boil it out?
No. leave it.
That's
Okay,
it.
leave it. Now, and you know, if your brain works better and says, okay, well, I really wanted to do y minus 9 equals 6 times x minus 3, could you start there
Yes.
and then go there?
Yes.
You can. However, give a little practice, and I don't think you'll even need to start there. I think you can do that in your head, right?
Mhm.
Okay.
If you don't want to start, I'm totally good with other people.
Well, I was just trying to figure out how well this connects and if I need to talk about it or not, but This just talks about vertical tangent lines. Since the slope of a tangent line is a limit, this would be a good place to discuss what happens when limits fail to exist. Okay? The slope of a tangent line might not exist because a limit doesn't exist. Discontinuity, vertical asymptote, oscillating functions that go up and down, because the tangent line has a vertical slope. Because what is the slope of a vertical line?
No,
There's 0.
that's 1.
No.
Whatever value.
0's in the denominator of the fraction, so what?
1, 0.
Officially, the slope is just undefined or no slope. Okay? Now, so in a case of a tangent line that exists but has an undefined slope, so when you have a vertical tangent line, okay, we use the following definition. And this should not surprise you. Okay, vertical tangent line, what's the slope of that? Well, it's undefined because it's 1 over 0 and it's got that vertical, so it's kind of, if we think limit, it's going to either positive or negative infinity. Okay, so a vertical line tangent to the graph of f, that limit is going to go to positive or negative infinity. And this is going to be when it happens to have some type of number over 0, right? That's when that is going to happen, is when your slope is some number divided by 0. Okay? Okay. Where am I at? Yeah. We'll call it quits there. Remind me to talk about normal lines, and then we will do some actual math there.
Lovely.
So we'll pick up at the top of the next page on Tuesday.
That is so.
Okay? You can start looking at homework a little bit, but obviously homework will be due on Wednesday.
Is there any that we can actually do?
There might be. I feel like there should be. We only have a page front and back left to go, so.
Yeah.
Ready for this test?